So after this subsection, you should be able to think about how certain experimental factors affect the chemical reaction rate. So things like the nature of the chemical reactant, its physical state, whether it's solid, liquid, or gas, the temperature, concentration, and whether or not there's a catalyst. So the reaction rate of a chemical reaction really depends on 5 kind of general ideas. The first is pretty intuitive, and that's just the reactivity. Things that are more reactive are going to react faster, and that's really just based on energetics. So an example of that is sodium metal and calcium metal. Both are actually similar. They react with water to form hydrogen gas and a base, but sodium, you can see when you toss it in water, reacts explosively because it happens so quickly. It generates a ton of energy as heat. Calcium, it reacts, but it sort of does this slowly by bubbling. If we look at sort of an energy diagram, remember energy is the driving force for all things in the universe. So if energy is a function of time for calcium and sodium reaction here, the initial states may be the same, but the final state for sodium is much lower than calcium. So the delta energy is a lot bigger. The driving force for this reaction is bigger, which means that it's more reactive and it happens faster. Second pretty intuitive idea is it depends on the physical state that's reacting. So these examples again, these are a chunk of solid reacting with a liquid. For a reaction to occur, they have to be in intimate, direct contact with each other. So if you have a giant chunk of sodium, the actual surface area to volume ratio is pretty poor. It means there's not much surface for it to react with. But if you have really finely grained powder like flour, then this thing is going to react explosively fast because there's so many sites for it to react. Similarly, when we add liquids together, they'll mix much more readily, and the physical state will drive the reaction to be faster. So most reaction rates also depend on the concentration of the reactants. That's simply because if you have more of it present, the number of collisions that can occur are going to be more frequent, and so you have a faster rate of reaction. Example of this is the acid rain destruction of marble. So marble is a form of calcium carbonate, which is shown in this picture here. H2SO3 is the stuff that forms in the atmosphere from industrial pollutants. And as that increases because of anthropogenic sources, then the decomposition of these marble statues increases as well. Fourth example is catalysts. So catalysts are these materials. They can be chemical reagents or they can be solids. The whole idea is they speed up the reaction. They make it faster. So an example of this in your real life are catalytic converters, which are all the rage these days. They're getting stolen off cars because they have a whole bunch of precious metals like platinum, palladium, and iridium in them. The whole purpose is to take exhaust gases, these things we don't want in our atmosphere, and to drive a decomposition reaction to tailpipe emissions that aren't so great but are still better than what was going in. And the last factor here is temperature, and this is another one that's obvious. The more temperature that you have, the higher the temperature, the more heat energy you have in the system, which means that those molecules are bouncing around faster, which means they're presenting themselves to make more collisions, meaning more opportunities to react. An example of this is why we store things in the refrigerator. The whole point of putting things in the refrigerator or the freezer is to slow down chemical reactions that cause food decomposition, like the decomposition of this apple here. So in the next couple chapters, we're going to talk about how to more quantitatively relate some of these perturbations to chemical reaction rate.